Good afternoon.
Good afternoon. I wanted to ask you a question. So for the examinations that the in-class test, what percentage is each one towards the final?
It depends. You have an in-class test
In December.
in December, and I think that counts for 15% of the module. You have an assessed practical in week 8 that counts for 20%, and you have some online tests that count for 15%. So that's the coursework, and then next year you have a 50% exam.
Okay, because before I got my timetable, my parents booked a holiday, so I don't know.
That is unfortunate.
Yeah. So I was wondering if I would be able to take the
Nope.
class information.
Sorry.
So thank you, sir.
Sorry about that. Good afternoon.
Can I leave this on your table just because I'm worried? Thank you.
I'm very worried. Good afternoon. Good afternoon. Most wonderful good afternoon.
That's what I thought, but all of a sudden it's a punch.
Good afternoon. Good afternoon. That's me. Good afternoon.
Charles Stimson, second 500. You kindly spoke to us at one of our dinners.
Of course, of course.
I wondered why the thousands were coming in here. Now I know. You're about to give a lecture.
I'm afraid so.
What on? Would I understand
Statistics.
it? Statistics? I wouldn't understand it.
Oh, absolutely. Absolutely. Statistics for first years,
Oh, really?
first session. If I'm absolutely 100% convinced that you would get it. You're probably
Is
a
that
mathematician.
100% being the
Yep.
proportion that you would give on
Absolutely.
your confidence
Well,
in my ability to
Totally.
understand?
Because you see, 95.4% of all statistics are just simply made up.
Yeah. Well, tell me when you have to go in. Did you hear the speaker that put down one of the members of parliament years ago who said 50% of the other party were liars? And the speaker said, you can't say that. So he said, okay, 50% of the other party are not liars.
Indeed, indeed. Good afternoon. Indeed, that is
You're
how
looking
it.
very well, and I'm sorry that I'm not joining you.
Well, if you are inclined, you can even watch it
Can I?
outside. Yes.
How do I watch it outside?
Good afternoon. It's live streamed onto YouTube
Oh, I see.
with a delay of about 1 or 2 seconds.
So it's always possible to watch lectures.
No, only mine.
Only yours?
Yeah.
Oh, well done. You're looking very well with it.
Thank you very much. So do you. I would like to see more of the second 500s this year. Would be lovely to get something going.
The others coming up because it's the Foundation Day celebrations.
Well, we have to do it. And you are graduating next year, aren't you? No, you did last. You
It was
did.
this year, it was this May.
Good afternoon. I'll see you around.
Cheers.
Good afternoon. Lovely. Do you have any other sessions after we finish today?
Just this 2 hour.
Just this 2 hour.
Is it 2 hours or what? There's two
Don't lead me into temptation, right? Right. Because I think 2 hours lecture slots are against the Geneva Convention.
I agree. Yeah, it's pretty good.
I mean, after 10 minutes, I lose the will to live.
Yeah, I don't blame
You probably as well, right?
I see how it is.
Wait, yeah, we can sit there. Yes.
Hi. Good afternoon. Good afternoon, everybody. Good afternoon, everybody. Don't break it.
Oh, there it is.
And I suppose it's not very useful for people who are left-handed.
Yeah. This is discrimination.
I'm just waiting for the first person to sue the university.
I should learn. No, but I could learn to do it for the money.
Sorry?
I could learn to be left-handed for the sue money.
Hello, good afternoon. 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 It is indeed.
Hi, Peter.
Hi. Good afternoon. Most wonderful good afternoon. Thank you.
Because you didn't finish.
Okay, let's make a start. Most wonderful good afternoon, ladies and jelly beans. How has your first week been? Amazing. Wow. I didn't pay you to say that, did I? Ah, okay. Everybody's sort of settling in? Yeah? Nothing too challenging? Of course, it is a different scenario to school. But, I mean, that's why you're here for. You're no longer school kids. You are now training as, hopefully, successful scientists. And, yeah, just something that I saw today on the group chat. It's great that a lot of people have joined. Somebody said, oh, I should not have said that on the group chat with Dr. Klapper being around on the group chat. He might take offense or something. No, he doesn't take offense, you know. It takes a lot for me to offend me, right? So don't worry about that. And I think the discussion was whether you should go to an induction session or not. To be absolutely honest, I'm not bothered whether you go to lectures or not. It doesn't make any difference to me. It makes a difference to you if you go to a lecture or not. But you see, most of you, not everybody, most of you are over the age of 18. So technically, you are adults. You can vote, you can drive a car, you can get married, you can do all sorts of things, right? You can make your own decisions. And who am I to argue with these decisions? So please do feel free to make the decision, as long as you also take responsibility for your decisions. I remember a couple of years ago we had a student who had a whopping 15% attendance. The student failed the year and then said, well, I'm going to sue the university because they didn't make me go to the lectures. And you think, facepalm. This is just, you know, what a, no, okay. And in what I want you to see, this university experience, and that's sort of an extension from what I said yesterday, what I want you to see this is sort of, it's here for you. You probably have heard this analogy with the gym. University is like a gym. It's there, you can train, but actually, if you want to get fit, you have to do the work, right? Now, I don't like gyms. I don't think I've ever set foot in a gym in living memory, as you can tell. I see it more like, you know, have you ever been to these eat as much as you can buffets? Yeah? So you pay 30 quid or so, and you can eat as much as you like. And I see university a little bit like that, right? You pay tuition fees. And then here is the buffet. You like chicken wings? Great, we've got chicken wings. You like kitten tikka masala? Yes, we've got that. You are vegan? No problem. Yes, here, everything is here. Now, some people choose to pay a lot of money and just take half a tomato and a leaf of lettuce. Fine with me, right? Is it worth the money? Probably not. So, we do the lectures anyway. Well, come along. Unless you have got something better to do, for example, kidney transplant or something like that. But we are here, and we provide you with all the goodies. If you want a doggy bag, yes. If you're a vegetarian, you can have a rabbit bag. Absolutely fine, yeah. So all there for you. So make use of it. And if you want any special catering, unless it is totally off the wall, we probably can do that as well. You want chocolate cake with pickled gherkins? Yeah, okay, can do that, no problem. Yeah, so tell us, we can do it. But make use of it. I think that's the most important thing. Okay, now sort of lecture over. So what I want to do with you today is get a little bit into data analysis, because in next week's practical and the week after, you probably, well, maybe not so much next week's practical, but in the practical in week 3, you will have to do a lot of data analysis, because that is what scientists actually do. We are constantly working with data, and we need to make sense of data. Yeah? And hopefully I will show you a few more or less interesting things, and with a little bit of statistics. I love statistics. Anyone else loves statistics? Hands up. Oh, not all at the same time, please. Right. Who hates statistics? Hands up. Holy McMolly. Uh-huh. Yeah. Why? Why? What's so horrible about statistics? It's boring. Or you can tell fantastic lies with statistics. You can cheat with statistics. 97.4% of all statistics is just made up. I told you that, right? And you can do really great things. We had the other day, we had a meeting where we got crime numbers, well, misconduct numbers. Students, the number of students who actually were caught smoking weed on campus. By the way, the university has a very strict zero tolerance to illegal substances. If you get caught and reported by campus security, it's a 200 quid fine. So either you don't smoke weed on campus, or you don't get caught. Yeah. Now, we were given these numbers, and there was then a comparison to the previous year. And they showed that the number went down by 30%. And everybody was, yes, hey, we did a great job. Campus security, they have noses like sniffer dogs. They're walking around. Oh, yeah, over there, somebody is smoking stuff. If you look at the data, it's all BS. There's no difference in the data. It looks like it's a 30% difference. But realistically, nope, no difference whatsoever. When I dared to point that out, everybody said, yeah, but the numbers went down. Yeah, so what? Right? You need to look at the data properly, like a true scientist. And that is what I'm going to do with you today. Right? Okay, so we are talking about data, about information. And first of all, we need to be clear about the different types of data. And you've done that ad nauseum. I know that you've done that because my son is currently doing GCSEs. And I assume most of you have done GCSEs or at least the equivalent to that. So, of course, you are all familiar with the different data types. We have, for example, nominal data. Yeah? Nominal data just simply means it's a label. We have ordinal data. Let me write that down. Let's see if it works. So we have nominal data. It's just a label. It is male, female, non-binary, for example. Yeah? These three groups. Facebook has 30 different genders and sexual orientations, but I don't want to go into that. So it's just nominal is the same as a label. And it has no quantity associated with it. We have ordinal numbers. And these ordinal numbers, they are sort of an order. So you probably all have seen what is called the Likert type questions. Strongly agree, agree, neither agree nor disagree, disagree, strongly disagree, right? This type of 5 scale. So there are numbers attached to it, but the difference between strongly agree and agree might not be the same as the difference between agree and neutral. So the difference between the categories is sort of not really very well defined. But we still can do something with these types of data. And when you do social sciences, for example, you will find there is a lot, many problems in social sciences are tried to be addressed through questionnaires, and they use these Likert type scales. Of course, we have interval data, and in interval data, you have in contrast to the ordinal data, the difference between one data point and another data point is very well defined. So, for example, the temperature scale, Celsius. The difference between 10 degrees centigrade and 20 degrees centigrade is the same as between 40 degrees centigrade and 50 degrees centigrade. So the interval is the same. What the interval data don't have is a true 0 point where there is nothing. Coming back to the Celsius scale, you could say, well, hang on, we have 0 degrees centigrade, right? But it doesn't mean that we don't have any temperature there. It's just arbitrarily set at 0, where the water usually freezes. Yeah? And last but not least, we have where we indeed have a true 0, and these are called the ratio data. So instead of the Celsius temperature scale, you can use the Kelvin temperature scale. And there you actually have 0 degree Kelvin. The 0 degree Kelvin means actually there is no temperature, because temperature in this case is defined as the movement of molecules of atoms. And if you don't have any movement, if everything stands still, then you have a true 0. So this is basically one way of ordering the numbers. And when you have numbers, you can also see them from a slightly different point. You can actually look at them either as continuous or as discrete data. What does that mean? Well, discrete data, you have fixed data points, and nothing is in between. So, for example, if I count the number of students here, I would always come up with a whole number, with an integer. So it might be 239 students. If another student comes in, it would be 240. Yeah? So there are fixed points. In this case, would it be interval or ratio? What do you reckon? Ratio? Why? Can I have 0 students? Absolutely, if you all bugger off. Yeah? So it could be 0 students, so it would be a discrete ratio. Can I have 239.5? Well, unless somebody is pregnant, but I think that we just discount that, right? On the other hand, continuous data, you see what I'm basically saying? Continuous data, there is something in between data points, or we even can't really say a fixed set of data points. So, for example, if I measure the height of somebody, it would be 182.356 centimeters or something like that, or 182.35 8 centimeters. And just depending on my measuring scale, it can be as many digits after the decimal as I like. Yeah, so it is really very continuous. And we will discuss how we treat that, this distinction today in this session. Right. Now, one of the things that you have done in GCSE is you have discussed the measure of central tendency. This measure of central tendency usually is described as either the mean. Very often you will find the word average for that. And whenever I use mean, I mean the arithmetic mean. There are other means. For example, other means? No? No. That's not a mean. We come to the median in a minute. The geometric mean, exactly. That's a different kind of mean, but we're not dealing with that. At least not in this session today. And for the arithmetic mean, you all know the equation for that, yeah? It's just simply you add up all the observations and you divide by the number of observations. So the mean, and I write it like that deliberately, mean equals, and I call each observation, I denote that with an x. So x1 plus x2 plus x3 plus, and so on and so forth, divided by the number of observations. Let's just simply call that n, the number of observations. That would be the arithmetic mean. The mathematical shorthand for that, you're all familiar with that as well, is something like that over n. And this thing here, this bit here is the sum symbol, or Greek sigma. It just simply means add all the numbers together and then divide by n. Okay? And we can do that. That's old stuff. Somebody said the median. This is also a measure of central tendency. What is the median? What is the median? Median? Median is just simply the middle number. When you sort all the observations in ascending or descending order, the median is the middle number. Let's just look at a simple experiment. And then surely this will become clearer. Let's say we have an agar plate. and we put some bacteria on it. Something like that. And we have another agar plate, also with bacteria on it. Let's say we have 4 agar plates. Let's say we count colonies, and we have 30, 40, 30, and 44 colonies. Okay? Can somebody quickly calculate what is our mean for that? How many? 35. 35, 36. Okay, let me do it in my head, right? 30, 40, and 30, that's 144, 144, 144 divided by 4 is 36. Is that right? Yeah. So the mean is 36. Now let's find the median for that. The median is the middle number. So let's sort these numbers. 30, 40, 44. Let's just simply come up with another number. Let's say 100. Just for the time being. Let's ignore then the mean in this case. So what is the median in this case? The easiest way is to, in a way, go from the left and the right side stepwise. So we have sorted them according to how big they are. 30, 100. 30, 44. We've got one number left. That's 40. So in this case here, 40 is the median. It's the middle number. Yeah? Does it make sense? Let's just quickly get rid of that, because we run into a problem if we have an even number. 30, 30, 40, 44. Okay, so 30, 44. Oh, we've got 2 numbers left. And the rule here is that you would usually then do the mean of these 2 numbers. So you find the middle between these 2 numbers, and in this case it would be 35, exactly. So it would be 35. That's the median. When is it useful to use the mean? When is it useful to use the median? Well, what you can see is, excuse me, what? Okay. Median 35, mean 36, right? Did you get that, Helga? Good. Okay, so when should we use what? Well, it really depends on what we want to do. That's always the case with statistics. But just imagine what I just had before with colonies. 30, 30, 40, and let's do 1,000. Oh, I forgot 44. Sorry, my bad. 44 and 1,000. Can somebody please calculate the mean for that? Two hundred and 220, 220, okay, 229, right? Because we've got colonies. Yeah? 229, that would be the mean. Very clearly, this 1,000 doesn't really fit into it, right? There's probably some data entry error or something like that. Very clearly, looks like an outlier. What is, in this case, what is the median? Loud? 40. Exactly. 40 is the median. So that is the mean. And that is the median. And what you see is the mean itself is very, very sensitive towards outliers, towards things that are way out, right? Whereas the median is not. The median doesn't care if there's one thing really big, doesn't matter, because we get rid of it when we go step, 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 step in. Yeah? So if we have something where the data are really, really weird, what should you do with that? What should you do with weird data? Eliminate outliers. Eliminate outliers. I love your suggestion. And yet, if you do that, if you eliminate outliers, you are a decent scientist. If you keep the outlier and you say, holy mackerel, what went wrong? Shoot, there is something weird going on. Let's investigate. If you do that, then you are a truly great scientist. Because surely there's a reason. Maybe somebody sneezed on that plate as well. Yeah? Or you discovered a new type of bacteria. Hey, how cool would that be? Right? So, be aware of outliers, but do not immediately say, oh, that does not fit my idea. That shouldn't happen. Don't discard them right away. But if you have to deal with them, be aware the median is not very sensitive to outliers. The mean is. And, of course, we have a third one, which is the mode. Third measure of central tendency. What's the mode? That is the number that turns up most frequently. So in this case, what would be the mode? 30. Exactly. Can you have more than one mode? Yeah? So, for example, if I have another 44 here, I would have what is called a bimodal case, bimodal distribution. SPY 2 with 30 and 44. And it's quite interesting because when you look at student marks, that's really interesting. When people write essays, exams with essays in it, what you usually see when you plot frequency versus grade, for an essay-based exam, you find probably something like that. How many modes? One. That would be the mode. There would probably be also the median and the mean if this curve is symmetric. That's essays. When I look at grades from this module, what I see is something like that. How many modes? It's 2. It's bimodal. So the first part, the first hump, that's those. Or let's look at the essay first. In the essay, unless you have a total writer's block or you have no idea what you're talking about, you will always be able to write something. So you will get a little bit of marks. You will never, ever really satisfy the examiners so that you get 100% in an essay. There's always something that you could have put in. That's why I hate essays. You probably as well. So that's why you get a sort of an average for your essay. It's you know, it's good. It's between 40 and 65% usually. And that's where usually the module average marks of my colleagues are located. In the case of, let's say, BI 308, you have 2. This bit here, the first hump, this is those students who don't get it, or who just simply don't want to get it, or coming back, who are just happy with half a tomato and a leaf of salad. On the other hand, hopefully you all will be in this position here, where you really get it, where you're close to 100%. Okay, you made perhaps some little careless errors. Shit happens all the time. You forget a unit, and I'm really, really tough on that. People who forget units, in my eye, are criminals. But I come back to that at another point. So this is a bimodal distribution. That makes sense? So far, not a big problem. Now we have another system where we measure of, what's the other one? Central tendency was one. The other one is dispersion. Exactly, thank you. Measure of dispersion. This basically tells us how far the data are spread out. How can you have two modes if their frequencies are different? That's a very, very good question. And that is actually sort of a matter of almost definition. If you see two peaks when you plot the data, then you can say, I feel inclined to say, right, it could be that there are two peaks, two humps, and by definition I can call that bimodal. And usually people say, don't go for more than two peaks. If you have 138 peaks, I don't know what the Latin word for 138 is, just simply doesn't make sense. So you can have, you can sort of define there are two peaks, and therefore I define two modes. I hope that makes sense to answer this question. So measure of dispersion. It tells us how far the data are spread out. And before I go any further with that and tell you what these measures of dispersions are, I need to talk a little bit about the difference between a sample and a population. And I'm sure you're all familiar with that. Because this difference will make a difference how we look at dispersion. Sample versus population. Now, let's say I want to measure the height of every adult in the UK. Or weight. Oh, let's do weight, because that's a particularly sensitive issue. Weight of I want to know the average weight or the mean weight of adults in the UK. So what I could do, obviously, is I go out and start weighing people. Would you be happy if I get my scales out and do a public weighing? No. Yeah. I wouldn't be either. And, of course, it would take a long time, wouldn't it? While I start weighing, it's about, how many people live in the UK? 60 million or something like that? Let's say 40 millions would be sort of adult age. Oh, it takes a long time to get this done. And some of them don't want to be weighed. Some of them live in, remote places like Tunbridge Wells, where you would never go there, right? Not out of your own accord. Do we have somebody from Tunbridge Wells? Oh, shoot. I'm so sorry. I like Tunbridge Wells. It's a lovely place. Yeah, please forgive me. Yeah, when you're in a hole, stop digging. So it would take a long time. Therefore, what we can do is we can just simply take a sample, right? So I just say, I get 100 people, put them on the scales, and measure their weight as sort of almost a proxy for the entire population. So if we think about it, population, we have that, and we take a sample. So that's our population. And that is our sample here. And whenever we talk about these two things, you probably will agree with me that they these are different things. Population, huge, potentially. Sample, much smaller. We indicate that also in the terminology. A population is characterized by parameters. And that's very fortunate because you have got population and parameters. So you can easily remember that. And abbreviated parameters usually use Greek letters. Bless you. Greek letters. On the other hand, a sample is characterized by, what is that called? What's the equivalent of parameters? Sample has statistics, and again, you can remember that very easily. Sample, statistics, and statistics are just abbreviated with normal letters, usually lowercase. So, we can say a population also has a mean, or can have a mean, an average. And here the mean for the population is abbreviated with the Greek letter mu. Like that, like micro. That indicates we have a population mean. A sample has a mean, and here we abbreviate the sample mean with something that if you are trying to type something on a keyboard, it drives you into despair because there is no letter for that. It is abbreviated like this. And it's called X bar. That indicates the mean of a sample. So when you see something like mu equals 80.5 kilograms, you know that we are talking about a population. If you see something like X bar, you know that we are talking about a sample. Now, when we are dealing with samples and populations, which one do you think is more accurate, gives us best information? Loud? The population. Right, population. Because in a population, we already capture everybody. Yeah? So there is no, we won't miss anyone. Whereas for the sample, there is a certain there's an uncertainty in it. Does that make sense to you? This uncertainty. And of course, if I, for example, say, right, I don't want to measure the weight of the entire population in the UK. Let's just simply do, I want to measure the average weight of all the students here, right? For one particular reason. Don't know what this reason could be, but just out of interest. So I could take samples. Okay, let's say I take a sample of the weight of 5 people. There are 5 people at the front. Could you all stand up for a moment, please? Yeah? Wonderful. So I could take the weight of these 5 people here, right, and calculate the average. So here the average x bar 1 would be, I have no idea. Thank you very much. Would be, say, A. Okay, now I could also choose another 5 people. Hey, there are 5 people over there. Could you stand up? Aha. Do you think the average from that sample is the same as the average from that sample? No. Thank you very much. Wait a moment. So we have x bar 2 equals B. Are these 2 samples, are they part of the same population of all the students in this lecture theatre? Yes, they are. So they come from the same population. But the sample means x bar 1 and x bar 2 are not the same. Are you surprised about that? If the average is not the same? No. It just simply can happen, right? Just by choosing people, yeah, by choosing my sample, and I would assume it is probably a representative sample, and that's another thing. A sample always needs to be representative of the whole population. If I, for example, want to measure the height of the population, and I go to the gym, and by chance there is just the basketball team there, this is probably not a very representative sample of all students, because usually basketballers are... Oh, by the way, can you remember what is the name of the what is the name of the New Zealand basketball team? Wow, you see, you learned something yesterday. And amazingly, you remembered it. How cool is that, huh? So, sample here. The samples are different. Yeah? The sample means are different. Did we make any mistake here in terms of measuring? No, actually, probably not. This phenomenon is called, any idea what this is called? It's called sampling error. I absolutely hate this expression because you don't make a mistake. It implies that you make a mistake, but there is no mistake. You did everything right, but sampling error just simply means by choosing a sample and getting the average or the mean of that sample, it will most likely be different to the average from a different sample. And that will be different from a third sample. So it really depends on your samples. You do everything right, but by choosing a sample, there is an uncertainty in it. Makes sense? How can we get rid of sampling error? Is there a way to get rid of sampling error?
Will you measure the whole population?
You're absolutely right. We could measure the whole population. In this case, we get rid of the sampling error simply because we don't have a sample anymore, right? But if we can't do it, if we can't measure the whole population, how do we get rid of sampling error?
Take a large number of samples, and then when you average those, then...
Oh, we could do that. I love that, because that goes down to the concept of what is called the central limit theorem. Yes?
A representative sample?
Representative sample, but again, representative samples, I guess you have been totally representative. We have got, for example, 1, 2, 3. 1, 2, 3 males, 2 females, yes, unless, yeah. You need to be so careful, you know, who you describe as, there was, only yesterday there was this thing in the news about the transgender man who gave birth to a baby and wanted to be named as the father of the baby, but the High Court ruled that, and okay. So I would say that's probably a representative sample. 3 males, 2 females, 2 females. So bottom line is, whenever we take samples, we will have a sampling error. Sampling error is like herpes. You can't get rid of it. Right? Once you've got it, you've got it. So that's sampling error. Whenever you take a sample, there is a sampling error. But the difference between these samples, if they come from the same population, any difference between the samples is only due to sampling error. So, so if they come from the same population, any difference there is only due to sampling error. Sometimes the sampling error is bigger than in other cases, but you have sampling error. It's always there. Now, I suggest we have a 10-minute comfort break, and then reconvene and carry on with the measures of central measures of dispersion and the equations for that. And also, I want to show you then how we can, from a sample, make conclusions about the population. So back in 10 for a comfort break. And if you want to go home, you know, there's no attendance register.
I was going to. I'll be back.
No worries. Just a quick question for you folks. Am I too fast? Am I too slow?
No,
you're
it's good.
perfect.
It's good, yeah.
Yeah,
Yeah.
it's right, the pace.
Perfect.
Thank you very much. Sorry? You're in a nice mood. I feel honored. I feel absolutely honored. Need to ask you as well. Is it too fast, too slow? Is it too... Is it all right? Okay, good.
Perfect.
No, perfect. Nobody is perfect, apart from me. But I'm actually intrigued. Why are you in a nice mood? Because it's Friday?
Very delirious. I've had enough sleep.
Okay.
I haven't got enough energy to move.
Fair enough. Fair enough. Yeah. Maybe if you tell your housemates that by keeping you awake, they avoid any tantrums.
I did have to cut the time for me, otherwise,
Okay, that was.
us any other modules?
You would be probably very disappointed when I say yes.
Oh no, I'm excited. I really like you as a lecturer.
Oh, thank you very much. Yes, next term I will torture you
Perfect.
with enzymes.
Okay, that's fine. Oh, I like enzymes. That's okay. I can't find too many notes online. Do you have any notes for skills for bioscientists, like this module? Because I have been excluded of a lot of things. I don't have a lot of stuff on my Moodle. There's been issues with my account.
Oh,
That's
really?
the only reason.
Have you spoken to the school administrator?
Yeah, they said that they were supposed to sort it out by the end of this week, so by today afternoon I should have everything.
Okay. You can look at all the stuff that I've done, for example, last year.
Okay.
Because I've recorded all the lectures last year. If you go to my YouTube channel,
Okay.
PK11 Kent,
Oh yeah, I wrote
you've
it
got
down.
that in the email, yeah. And whenever it says live stream, there is a lecture live stream.
Oh, okay. So it's like the same stuff that you're gonna.
Pretty much, but
That's
not in the same way.
perfect. Obviously, yeah, I understand that. Okay. Now
Makes
I can
sense?
put that, yeah. Thank you.
You're welcome. Okay, I think we've got everybody back, or most of you back. Or at least it is a very big part of the population that we started with, so the sample is pretty big, so that's good. So we said, obviously, if we take a sample, we will have sampling error. Stupid question. Population. Can a population have a sampling error? Of course not. But it's a population. Population is what, that's everything. Yeah? Sampling error can only happen with a sample. So obviously, we need to bear that in mind. Now, when we're talking about sample and populations, we just wind back for a moment. We said we have a measure of central tendency . What's that? X bar indicates it's the mean of a sample. And we said we can write this as the sum of all the observations divided by n. And I just simply can't be bothered with these little I equals 1 and n, and I just write it like that. Now, the good thing is, this is exactly the same equation. He's a G. Okay. This is exactly the same equation for this guy. What's that? The mean of the population. So you are in luck. you get 2 for the price of 1. You only have to remember one equation. The average or the mean for the sample has exactly the same calculation as the average for the population. However, if we want to look at how far spread out things are, we need to differentiate between the population. So let's do the population first. And a typical measure of dispersion is called variance. Basically, it tells us how variable our data are. And for a population, the abbreviation for variance is actually a squiggle What's that in Greek? It's sigma, and the variance is sigma square. So whenever you see sigma square, it means variance, and it tells us how variable the data are. And the equation for the variance is we take the first observation, x1, subtract the population mean, square it, plus second observation minus the population mean, square it, plus third observation minus population mean, square it, plus, you get it? We just add them all up. And then we divide by the population size. So that's the population size. We can also write this shorthand as sum of xi minus population mean squared divided by the population size. Make sense? So, why do we square it? Any ideas? Did you hear that? Loud. To get rid of any negative values. If there are any negative values, it would screw up the whole equation. But if you square a negative value, it becomes a positive value, and therefore it's no longer a problem. Absolutely right. Okay, let's say we have, let's do some weights. 80.0 kilogram, 81.0 kilogram, and 82.0 kilograms, just to make life easy for us. Can somebody please be so good and calculate the mean for that? And let's say that's our whole population. What's the mean? 81 kilograms. Now let's calculate the population variance. Sigma square equals 80 minus 81 squared plus 81 minus 81 squared plus 82 minus 81 squared divided by how many have we got? 3. So we have 80 minus 81 squared is plus 0 plus 1 divided by 3. So we have 2 over 3. Am I right? So you see how it's calculated. What is the unit? Why do we need units? Give you a quick example. Let me see if I find it. Would you like 20?
20 quid.
Would you like 20?
Yeah.
Yeah. Right, stand up. Trousers down? No. You get 20 of the finest on your backside, right? Because I did not state what 20. Yeah, got it? Would you like 20? What kind of 20? Yeah, you learned this lesson. No, you don't get 20 quid from me. Units. Units are absolutely essential. If I ever see anyone doing something without units, I will have a pink fit. Right? And you have red tears on your exam paper, if you know what I mean. Right? So what is the unit here for the variance? Loud? Kilograms? I like that idea, but no. Okay, let's put units in. We have, in the first one at least, 80 kilograms minus 81 kilograms squared plus, and so on. What's the unit? Loud. It's kilograms squared, the unit. You are absolutely right. Now, of course, this is a little bit weird. We worked with kilograms, and now we've got kilograms squared. So people don't like that. And therefore, they have introduced the concept of the standard deviation and this is just simply the square root of the variance. And for a population, it's just simply sigma. So the sigma alone means standard deviation. What's the unit of the standard deviation? Kilograms. Exactly. Because originally we had kilograms squared. So in our case, the population variance would be square root of 2 over 3 kilograms squared equals square root of 2 over 3 kilograms. And people are far more comfortable with that because the standard deviation has exactly the same unit that we have in our measurements. Yeah? That makes sense? Fantastic. So that was our population. Thank you. I'm glad it makes sense. God, I'm good. How can I live with myself? So let's look at a sample. For a sample, we also have a variance. Here, the abbreviation is S squared equals, and the first part is exactly the same as for the population. What we simply do is we add up the square of the differences, xi minus, what do I have to write here now? Sorry? X bar, thank you, why? You're right, why x bar? Because it's the sample mean, not the population mean. X bar squared. So that is the same thing. But here's the tricky bit. For the sample variance, we said the sample has always an uncertainty in it. We need to take this into account, that there is an uncertainty. In the population variance, there was no uncertainty. We could say just simply population size. But the sample variance, we need to take into consideration that there is an uncertainty, and this sample variance is larger than the population variance. So how can we describe that? And it turned out that a very good measure for that is we take the sample size, n, that's our sample size, and we subtract 1 from it, n minus 1. If you divide by something that is slightly smaller, your result will be slightly bigger. Yeah? And that takes care of this issue. So that is where this n minus 1 comes from. There are other reasons, but it worked out quite well. So this is the variance. What is the unit for the variance? For the sample variance? The same. It would be, in our case, kilogram squared. And of course, we can define the standard deviation for the sample. So here, S equals square root of S squared of the variance, sample variance. And in our case, if we look at it, well, we've calculated here this bit from the population variance. This we can keep. So that's 2. So let me write this here. That's 2. And our sample size was, if we treat that like a sample, it would be 3 minus 1. So that is 1. So in our case here, our sample variance would be 1 kilogram squared. And our standard deviation would be square root of 1 kilogram squared. And that, of course, is 1 kilogram. Population standard deviation we got as square root 2 over 3 kilograms. Sample standard deviation, 1 kilogram. Which one is bigger? Sample or population? The sample standard deviation. Absolutely right. A sample standard deviation is always bigger than the population standard deviation. Sample variance is always bigger than the population variance. If you have a very, very large number, let's say sample size is 10 million, your population and standard population variance will be pretty much the same as the sample variance, just simply because it doesn't matter whether you have 10 million or 10 million minus 1. But if you've got smaller samples, then this minus 1, something happens. Right. There is another measure of dispersion. And I know it's getting on, but let's do it. This is called the standard error of the sampling mean. And usually it is abbreviated as SEM, standard error of the sampling mean. SEM. It has sampling in it, so we only deal with a standard error of the sampling mean for samples, and it's defined as the standard deviation, the sampling standard deviation, divided by the square root of the sample size. And there are a few really funny things that you can do with the SEM. Okay, are you happy with that so far? Let's just quickly go back, rewind a little bit. Because that is the really important bit of this lecture today. I want you to change your thinking. Hopefully I can do a little bit of magic with you. Why on earth are we actually taking samples? WTF? Why don't we just simply go home and say, samples, yeah? Why do we take samples? Because we want, well, we want to, sorry? Save money. We want to save money, yes, absolutely. You're absolutely right. That's why we don't do the whole population. Oh, wait a moment. We use sampling. We take a sample, and from the information that we have from the sample, we want to make an educated guess about the population, right? Yeah? So, if I, for example, take the weight of 50 people, and I say, so my x bar equals 80.0 kilograms. Sample or population? Sample. Good. I take this sample and say, okay, my sample is about 80 kilograms. The mean of the sample is 80 kilograms. I do that because I want to know what the average of the population is. So, I want to make a conclusion. What is my population mean? This process is called inference. And this part of statistics is called inferential statistics. And if I've got a sample of 80 kilograms, average, I conclude that my population average is probably also 80 kilograms, or thereabout. Is it likely that from the sample that I have, let's say 80 kilograms, is it likely that the population average is also exactly 80 kilograms? Would you expect that? What do you think? I weigh these 5 wonderful subjects, and no, you're not 80 kilograms on average. You're probably less than that. Do we think that this sample average here reflects exactly the population average of everybody in the UK? No. But you probably will agree with me that it is more or less close, isn't it? Sort of within a certain wiggle room, within a certain interval. Yeah? So I can't be say for sure that the population mean will be exactly the same as the sample mean, but it will be in the same range. So I can write this as my population mean equals my sample mean plus or minus a few kilograms. Yeah? And this plus or minus is actually called a confidence interval. And this confidence interval actually depends on a number of things. The confidence interval depends on how sure I want to be. So let's say, for example, I say the population mean of everybody in the UK is 80 kilograms, of all adults in the UK, 80 kilograms plus or minus 80 kilograms. Does that make sense? Not really, doesn't it? Because it would mean I am fairly confident that the entire population, the average of the population weight, lies somewhere between 0 kilograms and 160 kilograms. So this would mean 0 kilogram. That is also called the lower bound. And 160 kilograms. That would be the upper bound. Now I can be 100% sure that that the average population mean is between there. So I would be 100% confident that it is within this range. What exactly it is, I don't know. That's sort of what I'm trying to guess. What about the average 80 kilogram plus minus 10 kilograms? So here, what would be the upper bound? 90. What's the lower bound? 70. So it would be between 70 and 90 kilogram. Do we think that is realistic? For the average, for the mean population? Well, if you go to Lidl and look at the weight of some of the customers there, you probably think, oh shoot, that's a little bit overweight, right? So again, it depends a little bit on your sample. But I think between 70 and 90 kilograms in the UK, this is not for the US, by the way. Sorry, do we have any Americans here? So we are, I'm fairly confident that we have that. But this is a reasonable range. And my magic now is, as a scientist, I want you to totally abandon the concept of having a fixed value. It doesn't make sense to say, from my sample of 80 kilograms, I think the population is also 80 kilograms on average. It doesn't make sense. What makes sense is that you say, from my sample of 80 kilograms, I believe that the average weight is between a lower bound and an upper bound. It is within a certain range, within what is called this confidence interval. Yeah? Are you happy with that? Always think in intervals, not in what is called a point estimate. Always think in intervals. Now, I want to give you a slightly more practical example. And we are going back to our plates. If I remember correctly, we had 30, 40, and 44 colonies on that plate. And somebody calculated that earlier and said the average is 36 colonies per plate. Question for you. What kind of data is that? Is that nominal? Is that ordinal? Is that interval? Or is that ratio? Ratio? Are you sure? Yes. Why? Can we have 0 colonies? Yes, we could have. So that is ratio. Excellent. Is it continuous or is it discrete? It is discrete data. We can have only whole number of colonies. We can't have a half a colony. So we have discrete data. And in this case, we have 4 plates. Is it a population or is it a sample? Careful, that's a trick question. Is it a okay, Paul, hands up. Who thinks it's a population? Hands up. 1, sort of half. Who else? 1, yeah. Who thinks it's a sample? Hands up. Who thinks, I wish he would stop now and I can go home? Yes. Just bear with me 10 more minutes, please. So if you said it is a population, you are absolutely right. If you said it is a sample, you are absolutely right. It is whatever you want. If this is all the plates that you are interested in, then for you this is a population. You are not interested in making any other inferences. It is just simply all there is. That's your population. On the other hand, if you are interested in, well, what would have happened if I had done 10 plates, 100 plates, 1,000,000 plates, an infinite number of plates, then this represents a sample. So it depends on what you actually want it to be. What is your intention to do with that things? And I know people always have good intentions, but you know, this is, so you need to be clear. Is it a population for me or is it a sample? Now, in this case, let's treat it as a sample, because that's more interesting. Sample. We actually want to know what would be the average number of colonies on basically an infinite number of plates, or in other words, in the long run. I always call that long run. Now this here, we have discrete data. These data are actually on sort of compartmentalized. The data, the number of colonies, are also independent of each other. The colonies don't know what happens on other plates. And a colony forms regardless whether there is another colony somewhere. This, to a statistician, would very nicely fulfill the criteria of a particular distribution and this distribution is called a Poisson distribution. Not Poison, it's a Poisson distribution. Poisson distribution has as a criterion, we are dealing with discrete observations which are independent of each other. And there are a few more criteria. For example, I'm standing outside the gents' bathroom and I count how many people go into the loo in a certain time span. This would follow, most likely, a Poisson distribution. So, within 10 minutes, 3 guys went in. The next interval, 5 guys went in 10 minutes. I deliberately chose a gents because my prediction is that it doesn't work for the ladies. Because, you know, from my own personal experience, I know that women tend to go in clusters. You go to a restaurant and all of a sudden, half the guests are moving towards the toilet. They're all female. And it's sort of, you know, oh, I need to go to the bathroom. And then I'm, oh yeah, can I come with you? Whereas with blokes, it's you know, I need to go to the loo. Oh, can I come with you? Really? So, this is a typical case of a Poisson distribution. It works with time span, and it works with defined volumes. So, for example, raisins in a bagel. They do these nice cinnamon and raisin bagels, which I'm particularly partial to. So if you want to bribe me. And you can count the raisins in it. And they are probably following a Poisson distribution. So how can we calculate the number of colonies in the long run? The equation for this Poisson distribution is very, very simple. It is C, that's the count, plus or minus a very, very special number. And this is a very, very dear number. I love that number. I have it in my heart. This number is 1.96. And where this comes from, I tell you in a different story. 1.96 times square root of C. So we have the count, and this one here, this part here, that is actually, that will be defining our confidence interval. So we had 30, 30, 40, 44 colonies, that's 144 colonies. We take them all together, we add them all up, 144 colonies, plus minus 1.96 square root of 144. I think I can do that in my head. So we have 144 plus minus, and instead of 1.96, I just simply do 2. Square root of 144, 2 times 12. So we have 144 plus minus 24 colonies. This was on the 4 plates. So we can say we have on 4 plates in the long run we have 100, and the count number would be between and I write that properly, and I want you to use that notation. square bracket 120 and 168. Have I done it right? Yes. So that's on 4 plates. On 1 plate, it would be in the long run it would be between 120 divided by 4 is 30, and 168 divided by 4, 42. So we would expect in the long run to find somewhere between 30 and 42 colonies per plate. Does that make sense? This is how you actually do this Poisson calculation. You use this equation here. You use this equation here. You calculate the upper and lower bound for the totals, and then you divide it by the total number, or the number of observations that you have. Right? What about, there is a caveat. There's a caveat. This equation here is only a rough estimate. It is not precise, but it gives us a sort of a good figure. This equation totally breaks down if the numbers are very, very small. And you then have to use slightly more the big guns, where you use a different kind of calculation, a different calculator. I will email you a link to that calculator if you really want to. Just one more thing, like Steve Jobs. What if we find on a plate 0? We have 0 colonies. How many colonies do we expect in the long run? So we have 0 plus minus 2 times square root 0. It's still 0, isn't it? And this is where it breaks down. Because in reality, if you do the Poisson distribution properly, the value for 0, and I write it as Poisson, would be roughly 3.7. So even if we have no colony, in the long run, we would expect anything from 0 to roughly 4 colonies. That is where this equation breaks down, where it doesn't work. But if the numbers are sufficiently big, then you can use that without any problems. Whoa, we've done a lot. In previous years, that was 2 lectures. 2 times 2. You are bloody good. Have a lovely weekend. You deserve it.